Let us study Cartesian sign convention used for spherical mirrors and lenses. Now here we can say that we people already studied how to draw graphs in maths. While drawing graph, you people are following certain rules. Let us see what is that first. Now we are drawing normal graph. So which principle we people are following, we'll see now. Here you see, this is the origin. Now this is the x-axis. This is the y-axis. Now here, this is the origin. Now its right hand side, we are taking it as positive. Which all values we are writing down, those values we are taking as positive. Here left hand side, which all values we are taking, that is taken as negative. Now here origin, its upward direction, which all values we are taking, that we are taking as positive. And origin's downward direction, which all values we are taking, that we are taking as negative. Almost same principle we people are following while drawing ray diagrams. So the principles what we are following for drawing the ray diagram, that is sign convention. We'll study what are sign convention. In detail we will study. Plus here now I drawn concave, this is convex mirror. Where polish is there, it's opposite side. Where polish is not done. Where painting is, this side paint done. So this side convex is there. So we can say that this is the convex mirror. Here this side paint done. So this side concave is there. So we can say that this is the concave mirror. Here now both the side inward direction is there. Concave lens already written here. Now this is a convex lens. Now here we people are studying convention, sign convention of spherical mirrors as well as lenses. Both of them. That means in case of mirrors as well as lenses, sign convention is common. So we will study the comparative study of sign convention of spherical mirrors as well as lenses. Now the first point, object. While drawing ray diagrams, we have to keep the object always at the left hand side in case of mirrors as well as in case of lenses. So we can keep the object here. I kept the object left hand side. It's also object I kept. Now left hand side, here I am keeping left hand side. Here again I am keeping left hand side. This is the right hand side. This is the left hand side. So while drawing ray diagrams, sign convention means some rules, some principles we have to follow. So while drawing ray diagrams, we have to keep the object always at the left hand side, either mirror or lenses. Now second point, that is all distances. Which all distances we are measuring from principal axis. This is known as principal axis. This is the principal axis. In all cases, the straight line which is passing through, that is principal axis. Here I can say this point, that is the pole of the mirror. This is the pole of the mirror. This is the optical center of the lens. This is the optical center of the lens. Now the straight line which is passing through the optical center of the lens, that we can say as principal axis. Now we can say that all distances measured, all distances parallel to the principal axis. Now here, which all distances we are calculating, that is parallel to the principal axis, we can say. This is the principal axis parallel to it. which all distances we people are measuring. Here also which all distances parallel to the principal axis we are measuring. Here again same, which all distances parallel to the principal axis. This is the principal axis. These all lines are parallel to it. Now we have to measure from these all the distances parallel to the rays parallel to the principal axis. Now their distance we have to measure from, in case of spherical mirror, from the pole. From the pole of the mirror, the distance we have to measure. So all distances parallel to the principal axis measured from pole of the mirror and optical center of the lenses. In case of mirrors, which all distances on which all lines parallel to the principal axis is coming. Now their height want to check. That checking is doing from the pole of the mirror, at the same time from the principal from the optical center of the lens. So once again the same statement I am saying, all distances parallel to the principal axis measured from pole of the spherical mirrors, optical center of the spherical lenses. Spherical lenses are concave lens as well as convex lens. Now the third point, distances right of the mirror. Which all distances are there? Right hand side. We can say that this is the right hand side. This is the right hand side of the mirror. This is the right hand side of the mirror. This is the right hand side of the lens. This is the right hand side of the lens. So what we are studying? Distances right of the lens taken, right of the mirror or right of the lens taken as positive. Distances right of the mirror or right of the lens taken as positive. Right side all values we have to take as positive. Distances right of the mirrors as well as lenses are taken as positive. Now this is the left hand side, this is the left hand side, this is the left hand side, this is the left hand side. Now distances left of the mirrors as well as lenses we have to take as negative. Distances left of the lenses taken as negative. Here also distances left of the lens we have to take as negative. Distances right of the lens, right of the mirror we have to take as positive. Distances left of the mirror, left of the lens we have to take as positive. Now one more thing. Distances perpendicular to the principal axis. Perpendicular to the principal axis. Here already perpendicular line I drawn. So again I am not drawing. Here also straight line is there. Then here again. So distances perpendicular to the principal axis taken as positive. So we can say that straight line, perpendicular line. So we have to take it as positive. Distances perpendicular direction from the principal axis, that we have to take it as positive in case of spherical mirrors as well as spherical lenses. Here also same way, perpendicular to. So distances perpendicular, here I will show you now. Distances perpendicular to the principal axis, we have to take it as positive. Here also same way, distances perpendicular to the principal axis, we have to take it as positive. Similarly here, distances perpendicular to the principal axis, that we have to take it as positive. Same thing here also. Distances perpendicular to the principal axis, we have to take it as positive. Plus one more thing we have to see, that distances perpendicular to the principal axis I said. At the same time we have to say that above the principal axis. Distance is perpendicular to the principal axis, I said. Plus one more thing you have to keep in your mind, that above the principal axis, then it is positive. Now distance is perpendicular to the principal axis, again I am saying, but that is below the principal axis. Here again, distance is perpendicular to the principal axis but below the principal axis. Similarly here also, distance is perpendicular to the principal axis but below the principal axis, then we have to take it as negative. Here also we can say that negative. Similarly here also negative. This is again negative. So we can say that distance is perpendicular to the principal axis, straight, either upward direction or downward direction. If it is upward direction, then we can say that that is positive. Downward direction, if we are taking the reading, then we can say that that is negative, common in spherical mirrors as well as lenses. Then the last point, that is focal length. Focal length of, this is concave mirror, this is convex mirror, this is concave lens, and this is convex lens. So focal length of spherical mirrors and lenses are, here we have to see that whether it is convex lens or whether it is concave lens, whether it is convex mirror or concave mirror. So when we study about the focal length of spherical mirrors, we have to keep in our mind that we have to see that whether it is convex mirror or whether it is convex lens. If it is, again, whether it is concave mirror or concave lens. If concave mirror as well as concave lens is there, focal length in case of concave mirror as well as concave lens. Focal length in case of concave mirror and concave lens, then it will be positive. In case of concave mirror as well as concave lens, their focal length will be negative. In case of concave mirror and concave lens, it will be negative. Focal length of concave mirror and concave lens will be negative, and focal length of convex mirror and convex lens will be positive. These are the Cartesian sign convention. We'll move roughly once again. The first thing, object we have to keep at the left hand side of the mirrors as well as lenses. Second thing, all the distances parallel to the principal axis measured from pole in case of spherical mirrors, optical center in case of lenses. Third thing, distances right of the mirrors as well as lenses counted as positive, left of the mirrors or left of the lenses taken as negative, distances perpendicular to and above the principal axis taken as positive, distances perpendicular to and below the principal axis taken as negative, focal length of concave mirror and concave lens will be negative, focal length of convex mirror and convex lens will be positive. Now we will study three important terms. Along with that, three important formulae. The first one, what is lens formula? Lens formula means what? Lens formula is the formula which is showing the relationship between the image distance, object distance as well as focal length. So once again, what is lens formula? Lens formula is the formula which shows the relationship between image distance, object distance as well as focal length. So we will study its formula now. Here lens formula is equal to, lens formula I am doing now here, 1 upon V minus 1 upon U, that is equal to 1 upon F. So here we can say that what is lens formula? Lens formula is 1 upon V minus 1 upon U is equal to 1 upon F. Now here the object distance, anywhere, whenever we people are drawing a ray diagram by using lenses, object anywhere you can keep. That means if you are keeping between optical center as well as principal focus, or at principal focus, or between principal focus, that means f1 and 2f1, between that or beyond that, or at infinity, anywhere if you are keeping object, the lens formula will be same, that is 1 upon V minus 1 upon U is equal to 1 upon F. Now we will study what is magnification. So magnification, it's a formula we have to study now, and it's a definition. Now what is magnification? Magnification of a lens is the ratio of height of the, then magnification, it's a symbol I am writing as capital M. Magnification of a lens is the ratio of the height of the image to the height of the object. So height of the image, that I am writing as H2. First I will write in word, height of the image to the height of the object. Now same thing in the form of here, height of the image we can write as H2, height of the object we can write as H1. Then how the formula will be there? M is equal to, magnification of the lens is equal to H2 upon H1. Or one more way we can be able to explain it. What is that? Magnification of a lens is the ratio of image distance to the object distance. So we can write as, now same thing I am writing here, image distance upon object distance. So again I am writing as image distance we can write as V, small v, and object distance small o. So sorry, object distance small u. Now we can write here M is equal to H2 upon H1 written, or we can write as M is equal to V upon U. So here now magnification of a lens is the ratio of height of the image to the height of the object. Height of the image to the height of the object, or we can write as distance of the image to the distance of the object. Now instead of writing such a word form, we can write in the form of formula. What is that? M is equal to H2 upon H1, or M is equal to V upon U. Now one more term, that is combination of lenses. Now what is meant by combination of lenses? If you are getting lenses which has f1 focal length and f2 focal length, that means you are getting two lenses now. One is having focal length f1, other one is having focal length f2. Now both of them, if we are keeping close by, two lenses we are keeping close by, then what will be the combined focal length? For finding combined focal length, we can use one formula, that is 1 upon f is equal to 1 upon f1 plus 1 upon f2. So we can say that here now focal length of the combination lenses is equal to, or focal length of combined lenses is equal to, what is the formula? 1 upon f is equal to 1 upon f1 plus 1 upon f2. Now a quick revision, that is first one, lens formula. If lens formula will be there, you have to keep in your mind that object distance, image distance and focal length. Now the formula of lens formula is 1 upon v minus 1 upon u is equal to 1 upon f. When we are thinking of magnification, there you have to keep in your mind height of the image, then height of the object. If you are getting height of the image and height of the object, for finding the magnification, h2 upon h1. h2 is the height of the image upon height of the object h1. Or distance of the image, that you have to take it as v. Distance of the object, you have to take it as u. So then the formula magnification m is equal to either v upon u or h2 upon h1. Now other formula, that is combination of lenses. For finding the focal length of combined lenses or combination of lenses, you have to consider two lenses which are having focal lengths f1 and f2. Then the formula how we can write, 1 upon f is equal to, that means focal length of the combined lenses is equal to, that is 1 upon f is equal to 1 upon f1 plus 1 upon f2. What will be the combined power of two lenses which has P1 power and P2 power? That means the power of one lens is P1 and power of second lens, that is P2. If we are keeping both the lenses close by in combined condition, then what will be the combined power of both the lenses? For finding that, we can use one formula, that is P is equal to P1 plus P2. So combined power means joined power of two lenses. One is having P1 power, other one is having P2 power. Both of them we are keeping close by. As a result of it, their combined power is equal to, which formula we have to use it? P is equal to P1 plus P2. Now we will study parts of the eye, parts of the human eye, as well as functions of each and every parts of the human eye. So we can say that first, this is the outer cover of the human eye. We can say that outer cover of the eye, that is very transparent. So that transparent outer cover of the human eye is known as cornea. This is known as cornea. Transparent outer cover of the human eye. We can say that inside the eye, outer part, that is known as cornea. It is very transparent. Through that, light rays are passing into the eye, or we can say towards the eye lens. Now inside that cornea, you can find that a dark colored part. We can say that this part is known as iris. This iris is having different color. In case of different people, different colored iris you can see. Here means a black colored, maybe brown colored, maybe green colored, maybe like that way different colored iris is seeing in different people. Now at the central part of the iris, at the center of the iris, there will be a hole. That hole is having the capacity to, hole means it is round shaped one. It is having the capacity to increase its diameter or decrease its diameter. In case if there is bright light is falling on the eye, immediately the diameter of the hole will reduce. At the same time, if dim light is falling on the eye, immediately the hole's size will increase. So we can say that this hole is having the capacity to change its diameter. Change its diameter. Either it can increase or decrease its diameter. Now we can see that this hole is there. Sometimes its size may become little larger. Sometimes its size may become little smaller. So this I am making little more medium. So here we can say that this hole, the hole which I made here, its size can increase or its size can decrease depending upon the intensity of the light. Either it is bright light or dim light. If it is bright light, then its size becomes small, it contracts. At the same time, if it is bright light, if it is dim light, then its size expands, increases. Now such a hole, this hole we can call as pupil, P-U-P-I-L. This is the eye lens. Eye lens is known as, eye lens speciality is crystalline. Crystalline eye lens we can see. Crystalline, crystal-like, crystalline eye lens. So here it is a muscle only. It is a muscle and we can say that it is transparent. So it is not got the name as crystalline eye lens. Now we can say that this eye lens is connected with the help of some muscles. That muscle is known as ciliary muscles. Ciliary muscle. Both the side you can find that ciliary muscle is there. With the help of ciliary muscle only, the eye lens is remain in the fixed position. This is now we can say that a cut is there. That means a transverse cut is there. Round it is like a ball it is there. So from all sides in a fixed condition the eye lens is holding with the help of ciliary muscle. Now this coat, outer coat of the eyeball, that is known as sclerotic coat. Sclerotic coat. This outer cover of the eyeball, eye itself is like a ball. It's one section that is only shown over here. Now we can say that this outer cover, that is known as sclerotic coat. Now it's inside one more coating you can see, that is known as choroid. Choroid. Now this is the inner coat we can say, inner lining of the eyeball, that is known as choroid. Outer cover of the eyeball, that is known as sclerotic coat. Now we can say that this is known as, here some nerves you can see, this is known as optic nerves. This is known as optic nerves. Here one disc-like structure you can see, the whole thing. This disc-like structure is known as optic disc. Optic disc. Now here some muscles you can see, that is known as muscles. So here also muscle is there, here also eye muscles are present. We can say that this is the eye muscles. Now here you people already studied the structure of the eye. Now one speciality is there, this eye lens. This eye lens is having the capacity to change its focal length. Change the focal length means adjust the focal length. Change the focal length. Its meaning what? Or we can say that it is having the capacity to adjust the focal length. So we can say that eye lens is having the capacity to adjust the focal length, or we can say change its focal length. Now when it is changing, that we will see. If the object is very far, or if the eye want to see far away object, that particular time this eye lens, it flattens. If want to see far away object, eye lens flattens. As a result of it, focal length of the eye lens increases. Focal length of the eye lens increases. As a result of it, the normal human eye can see the far away object. So when a normal human eye is there, such a person, normal human eye, it's meaning what? No defect is there, no problems are there. No, what we can say, far away object is seeing problem, or no nearby object is seeing problem. Such people, we can say that in their eye, the eye lens is having the capacity to adjust its focal length. We can say that it is having, it functions automatically, we can say. It functions automatically. That means a human eye lens functions automatically. On its own, we don't want to do any screw tightening or loosening work. So it itself functions. How it is? If it wants to see far away object, then immediately eye lens flattens. As a result of it, its focal length increases. Then it can be able to see the far away object. If it wants to see the nearby object, that particular time eye lens becomes rounded. Eye lens becomes rounded. As a result of it, focal length decreases. Focal length decreases. As a result of it, it can be able to see the nearby object clearly. So we can say that in our eye lens is there. That eye lens is having the capacity to change its focal length automatically. As a result of it, without any strain or any stress, we can be able to see the nearby object as well as far away object clearly or distinctly. Distinctly means clearly. Distinctly, it's the meaning clearly. So for seeing nearby object as well as far away object, in the eye lens itself is having some adjustment. As a result of it, we can be able to see the far away as well as nearby object clearly. One more thing labeling I forgot, that is here one screen is there. This screen is known as retina. Retina. There is a screen at the opposite side of the lens in the eyeball, that is known as retina. Now one more thing is there, as and when the object is there, suppose object is nearby or object is far away. So the rays of light passing through the eye lens, afterwards as a result of it, on the retina an inverted image will fall, or an inverted image of the object will form. So here we can say that on the retina there will be the formation of an inverted image. There will be the formation of an inverted image. Where? On the retina. As and when there will be the formation of inverted image, what will happen? As and when light falls on this retina, the retina will send electrical signal to the brain. So here already now inverted image formation is taking place. As and when the light rays passing through the eye lens from the object. As a result of it, we can say that here the image formation will be taking place on the retina, but that image will be in which condition? In the inverted condition. As and when light falls on this retina will be very much excited, very active. As a result of it, this information with the help of optic nerves, it will reach us to the brain. Brain studies about it, analyzes means studies about the electrical signals sent by the retina towards the brain through these optic nerves. After that, after studying that, the brain will send the message into the retina as well as into our eye. As a result of it, we are able to see the object, how it is looking same to same. So first image formation will be taking place on the retina in the inverted condition. But after studying by the brain, we are able to see the image, or we are able to see the object, how it is looking same to same. So image formation here on the retina is taking place in the inverted, but when we see it, that particular time brain is sending information to us. So as a result, or to our eye, as a result of it, we are able to see the clear image, or we can say that real photo, real picture of the object with our eye. Thank you.